Okay. I didn't let you in earlier because I was still in pre-cal, but now we're in
Okay.
cal. I'll be right back.
But it didn't say it was gonna rain.
No, this early morning it said it was gonna rain, but then they changed it because of sun. So I'm pretty sure they just look outside and let the side.
Right. Is somebody trying to join? Oh, can I let them in?
Yeah, you can let me
You should ban him.
I don't want.
Ban visit.
Yeah,
Ban him.
ban him.
Ban him.
I don't think I can.
You showed up in my
I mean, you can always.
Wait, which one I press?
No, you did it.
Oh, hi Ryan.
Right.
Louis, don't shake your head.
It's
not showing his face.
Hi.
Ryan.
Ryan, you wore your shirt today.
You're in uniform.
What is this? Oh, is this where you
Yeah.
draw?
Yeah.
That's so cool. How do I go to the left? How do I go to the left?
So the what? Good job.
Like,
Take your mask off and say hi. I can see your face.
If I find you or your, all that Connecticut music. I know, I don't know what it is. I was gonna do stuff. This is, you can only be transferred, I'm punching warm air towards you.
Okay, I'm gonna go to another page and take roll. So y'all excuse me for a minute.
Easy to do the whiteboard thing on there or hard?
It takes some getting used to. I'm getting better.
It seems like it'd be fun.
By the time I get used to this, we'll be moving to the new building and I'll have some new technology I have to.
Wait, have you ever seen a smart board?
This is
It's like a
physics.
whiteboard, but it's like digital and it's cool, like imagine what you
There's an option now
But
for
it's a whole
virtual.
board.
Yeah.
So I could just come and grab a pen here and like.
Ava here, Madison, Cameron is still absent, right?
Wait, but how does it work?
It's on in history.
Virtual.
Yeah.
Virtual. Okay, there. Pilot, yeah.
So it's like a whiteboard.
Has Cameron been in any of the classes? She has been, or then maybe that was her
Oh, you.
ringing the bell.
Isn't that cool though? They have, like,
Yes,
all
it
these
is,
pictures.
isn't it?
And then you can just erase it easily.
Yeah.
Ding dong, this is, okay, so Cameron is virtual.
Okay, bring them back. Bring them back. Put them up there. I want
I'm
you to
going,
decorate
just let me take a roll.
them. I want to decorate them.
I'm gonna decorate them. Okay, so hang on, let me maximize them. Ah, wait a minute. Oh, there you go.
Oh, it went away.
Okay, y'all gotta sit real still so that they can draw you on the whiteboard.
I don't know, you pick one. I'm doing my own thing.
No,
Oh, wait, no, you can just show it.
Yeah, they can see you doing it.
Drawing them?
Take it. Devil ears.
Oh, that's a mountain behind you.
Can they see?
Oh, it's
it?
wings. I gotcha.
Am I supposed to
Okay.
be an angel?
Madison, you're doing your own thing. I'm doing my thing.
I'm doing.
How do you?
What should I do? What should I do? The devil? Yeah, like. Okay.
Give him a face. Oh, tail too.
Brian, don't move.
What should we do for camera?
Yeah, let me turn the light off.
Give him, yeah. We have to be nice to Cameron though. Cameron, what do you want to be?
Put little Oh, she's got dark background, so it'd be hard to see anything to
It
show.
doesn't matter.
You could turn it.
You give her some glasses.
It's
It's a little tear tattoo.
We can make it
on
funny. Oh yeah, make her a bunny. I want a tear tattoo. Okay. Don't move, Cameron.
No, it's supposed to be at the corner of her eye.
At the corner of her eye? Okay,
Yeah.
don't Cameron, don't move. Don't move, don't move. Okay, wait, stop.
There you go. Oh, give her a nose ring.
Oh,
Some piercings.
you can't move.
Okay, and some eyebrow piercings.
Oh, wait. There we go. Hold on. Oh,
Cameron,
Cameron,
don't
That'd be a good way to test
stop. Okay,
something.
stop. I'll show you this one. Oh, you can't really see on him.
I got it.
I like the bunny ears.
Pink now, little, there we go. Now, wait, we could give her a little Marilyn Monroe thing. Who is that?
There we go.
All right, I'm done. Got your race.
Aw.
Quit vandalizing your classmates.
Okay.
I was like, what else are we doing?
Okay, so I am going to share the screen. Figure this out. That, put it up there. Okay, so turn to page 143. We were talking about gravitational potential energy and kinetic energy yesterday, and I worked a problem. You'll get plenty of chances to work some problems there. And then at the bottom of page 142, it starts talking about mechanical energy. And it says, for macroscopic systems, mechanical energy refers to the sum of the orderly potential and kinetic energy present in the system. In other words, your kinetic energy plus your potential energy. Like right now, your kinetic energy is 0. If we use the ground as our level, our ground level, then your potential energy is 0. So your mechanical total energy is 0. But if you started levitating, then you'd have some potential energy. And if you started moving, then you'd have kinetic energy. You would add all that together, and that would be your mechanical energy. And it says that it's of a particular significance, and we'll come back to it in section 531. So that's all he says about that. And then we go to elastic potential energy. So that's where I want to look at, which is on page 143. Elastic. And I need to probably move a little bit more over this way to get out of your way. Here we go. And this affects anything that stretches, like a spring or an elastic band. I think every time that we use it, it has to do with a spring. The slinky or whatever, okay? And so at first they give us an equation called F equals K delta X. Now this has nothing to do with the potential energy yet, okay? So what this means is, say you have a spring and it's holding up some box or something here. And you pull it down this far, okay? From here down to here, you pull it. Does that make sense? So that distance there is delta X. And the force that you had to pull to get it down is equal to the F, okay? That's force. And then this K here is called the spring constant. Well, let's go back and redo some of that. Undo. Constant, there we go. And so the first thing we normally have to do is figure out what that spring constant is. Distance, what does say distance there? And so like they'll give you something, they'll give you a problem like on the bottom of page 143, they say spring, example 5.3, 6 centimeters in length. So we're going to just say L1 is 6.0 centimeters. It's hanging vertically from a hook, a 100-gram mass, and it has another decimal 0, so it's more significant digits. It's attached to the end of the spring, stretching the spring to a total length of, so I'm gonna, up here I'm gonna put L2, a total length of 8.5. Determine the spring constant of the spring. Okay, so if length 1 was at 6 and length 2 is at 8.5, what is delta x? In other words, I could have put x1 and x2, and then just subtract. Does that make sense? And so it went a total of 2.5 centimeters, right? Everybody see how I got that? Okay, I'm gonna draw a picture of it. So. And then you went doing, 7, 8, 9. So it went to there. Because now we have an extra 100 grams. Okay, so this is, that's 6, 7, 8, 9. So right here at 8.5. And this was at 6. And so it went from 6 to 8.5. So that distance in there, delta x, is your 2.5 centimeters. Okay. And the force to pull it down, what's our formula for F equals what? MA, but if it's the weight of something, it'd be mg, right? Because it's the force due to gravity. And so in this case, the force is 100 grams times 9.8, or 980. Oh, dang it, that's not right, because I have to have kilograms there, right? I'm just gonna take the eraser and erase all this for now. I'm gonna go back down to here. M equals 100 grams, which is the same thing as 0.1 kilograms. And then F equals mg. So that's 0.1 kilograms times 9.8 meters per second squared. So you get 0.98. What's the unit? Newtons, right, okay. And so now we go back to our equation, F equals K delta X. We're trying to find what K is. So K would be F over delta X. So that's the first thing I do, is they give you information to figure out what K is. So in this case, we got 0.98 over delta X. We said 2.5 centimeters, but what's that the same as? 0.25 meters. Remember, we have to have MKS units. So over here, we're going to have 0.25 meters. And so K is equal to, hopefully they did the work here, 0.025. What? Yeah, I was wrong. This has to go over twice. So it's right there. Erase. Erase. A little crazy there. 0.025, and so we end up with, oh, I did the wrong thing here too. It's been a long day. Okay, so they tell me on page 144 that 0.98 divided by 0.025 is equal to 39. Of course, obviously. And what are the units? N over M, newtons per meter. That makes sense. It took 39 newtons per, like if you were gonna use the same force to get it to stretch a whole meter instead of just 2.5 centimeters, you would have had 39 newtons for the whole meter, I guess. I don't know. But that's the spring constant. Okay, and once you know that about a spring, then you can predict how far it's going to move depending on what force you use or what force you used if you know how the distance was, which is what they do, I think. No, they don't, but they will. Okay, now finally, they finally do get to an equation that involves energy. Whoop, okay, let's go to red. And they call it UE. Okay, the elastic potential energy. It's sort of like kinetic energy, which was 1/2 mv squared, right? Well, it's 1/2 k. Instead of v squared, it's delta x squared. Isn't that interesting? I think it is. What is all this? Okay, UE is elastic potential energy, or elastic energy, you can just say that. Remember, we're using U for energy. And so E for elastic, because earlier we had already had, let me go back over here, that UG was MGH, and you put that on your formula sheet, and then we had UK was 1/2 mv squared. And then we also had already had the power formula too. So if there was anything else we had to have. We had an efficiency formula and a power formula. Okay, so make sure all those are on your formula sheet. Efficiency is blah, blah, blah. And then you had power equals U over T. And now we've got this one as well. And so what if we wanted to know like when you stretch this out, I guess I'm dealing with this one on the right here. If I was to go back to this situation and ask myself, okay, I've got, the spring is stretched out, so it's got potential energy. If I let go, it's gonna bounce, right? So it's got some potential energy in there. If I wanted to calculate the amount of potential energy, I could put my K of 39 right here, 39 for K. My delta X would have been 0.025 in there, and then 1/2, and then I would find the amount of joules in there. Does that make sense? No, this blurry in here, apologize. I don't use this space very well.
Could we do that, like, get a real quick visual graph?
Yes, so y'all go to the board. We're gonna give it a shot. I'm going to clear this off. Is everybody done with this? Okay. Go to the whiteboard. You guys at home, go to a piece of paper. Okay. Somebody stacked them in a little pile. Okay, if you have your book, but you don't have to, I'm on page 164, number 20. Okay, so a certain spring, I'm gonna draw it, is hanging freely, as it just hangs freely there, has a length of 35 centimeters.
Wait, there's something on the sheet?
Not yet. We're just letting it just hang, dangle there, okay? And then when a mass of 3.75 kilograms,
What?
a mass of 3.75 kilograms, when that's hung on there, when it's attached, its length goes all the way to 41.5 centimeters. So determine the spring constant. What is K? So do you remember what the formula is? F equals, no, we're not using that one yet. We're using F equals K delta X. Delta means a change in, so how are you going to find the change? K equals F over delta X, right? And we got to make sure we're using MKS. So I'm going to go over here to do delta X. So delta X is going to be 41.5 minus 35, right? Is it 35 or 3.5? 35.
It's just to make X different from other X's. Think of it as formula.
Sometimes they actually give you delta X straight out, and other times you have to calculate it like this time. So in this case, we're trying to find K. Okay. So you first you have your equation, F equals K delta X, and you solve for K. Okay, then you have to find out what the force is. Well, I'm finding what the delta X is first. And so I subtracted these two numbers,
Delta X is going to be L2 minus L1.
which was 66.5 centimeters, which is 0.65 meters, right? No, I did it wrong again. I move it over twice, it's 0.065 meters. What?
What's the unit? Is it?
You got 0.035?
I mean, I changed these to meters.
And then subtracted?
It's point.
Wait, 41.5? Where's your 41.5?
I don't know where you're Can I throw it?
You pass it down. Oh, you said, okay, the original length was 35 and then it went to 41.5.
Oh,
40.
31.
Oh, sorry.
Wait,
I haven't
you
got an answer for it. I
subtract?
did that.
Okay, so it's the
Yeah.
41 you subtract, not the 35.
Right, right here. Because it's always L2 minus L1. Okay, then I gotta figure out what the force is. Well, the force is equal to the weight. These are the same thing, right? The force is equal to the weight, so what's 3.75? Times 9.8. 36.75.
Wait, do you change?
So you needed to change centimeters to meters, but they already gave you kilograms, so you didn't have to change that. But you did have to convert it to the force by multiplying it by G.
Wait,
What did we say?
wait, so you can keep the kilograms?
Yes, because MKS, you want meters, kilograms, seconds.
Okay.
Did y'all get 565? That's a huge.
I'm so bad.
0.4, we'll just leave like that. Newtons per meter.
Not a true constant because we're.
Now don't erase that.
Well, it's a constant, but that's our equation.
Oh, I already erased
Okay,
it.
well, I have it on the board. Okay, now we're gonna continue on to number 22. I mean, 21.
Like, wait a minute.
Oh, wait,
Never
we're
keeping it?
Yeah, we're gonna keep going.
It's okay, she has it right
And what color should I go?
Yes, but they don't have a pretty pink. You do like light blue.
Light blue.
here.
Yes.
Okay.
Science.
21.
Gosh, it's so pretty.
You see it? It's all blurry down there, isn't it? Sorry.
That's
I could erase. No, I don't want to erase. Okay. So it says for the spring in the previous problem, determine the elastic potential energy, which is UE. If the spring is compressed to a length of, we'll call that length 3, 29.1 centimeters. It says compressed to, so this time you're compressing it, but that's still, you're gonna go from 35 to 29 centimeters. 29, read that right? 29.1, sorry guys, did I say that? 29.1, okay. Okay, so it goes, basically you're gonna take the, I guess they're gonna want negative numbers, I guess, yeah, because this, let me undo. So you're gonna use the 35 centimeters, and then it goes to 29 centimeters. So you need to find the difference between those.
So you need a new delta X.
Yes. And remember, UE is equal to 1/2 K delta X squared.
So it's okay if it's negative.
Yes. That, yeah. Let's see if he gets it in negatives.
Well, it would, because this is squared, it would end up going away anyway.
Oh, you're right. So I'm just gonna not worry about the sign on that. 5.9. Did you change it to meters?
Is that gonna be newtons for our answer?
No, what's energy always in?
Joules.
Yeah.
I feel like my students always look at their greens on. But they're always kind of like a greenish yellow. It's really gross. What happened?
Yeah, I got 0.98
Yeah.
joules. And I looked it up and that's what the book had.
Is it nano?
Ava's covering up for the joules. You want to do another one?
Yes. We love math. What number was that? 20 and what?
21.
This was 20 and 21. Which does not necessarily mean you can write DOB.
But I'm doing it right now and I'm using my brain. So why should it count?
Copy mine.
Who said so?
I use my brain.
I
used my
You can DOB.
I
No,
also-
y'all can all DOB it. Okay, we're gonna clear drawings and go to 22. Do I still stay with the pretty blue?
Yeah.
Wait, no, change it.
No,
Make it a different blue. The blue above it.
Yeah.
Blue above it.
Yes, I like
Oh,
that.
shine that, okay,
One of
shut
my
that.
favorite good blue.
Okay, determine the force
Look how clear it is.
required to stretch the spring 12.0 centimeters. If it stretches at 12 centimeters, they're not giving you an L1 and an L2. They're giving you the actual delta of the delta X. Okay. So what figure out the force required if it stretches 12 centimeters and the spring constant is 175 Newton per meters. Well, that's pretty simple. I'm not even gonna work this one. Let y'all do it.
She's not using her brain. That's why. That's why she went.
Oh, wait, I know how to do
You
this.
know the formula, right?
Make it right.
Wait.
Please don't tell me I got it
I
wrong.
don't even know.
That's so easy. If I got it wrong, I'm gonna be so heartbroken.
Did you multiply it in your head?
Yeah. No, I put on my calculator.
Oh, okay.
Boys, huh?
Did you?
Girls only.
That's right. We're liking it. Actually, hang on a second. Let me show you.
I have a question.
We got some guys. And this is
Over there.
Cameron, yeah. We have, just so they can see you, we have Mr. Lockyer visiting.
Sorry.
You can, but good luck trying to find me.
Okay.
I got a meeting after school. So if you give me before 3:45, like right after school.
Okay, I haven't done the math. Did you find the equation? Okay, put it down.
Oh, maybe.
I can't read. What is it?
What do you want?
I think it's
Okay, so we're doing, F equals,
I didn't do that one.
okay, so let me go back to sharing the screen. Okay, so the equation was, if you forgot to write it down,
Wait, what was it 21 joules?
I haven't done it yet. K delta X. So,
Oh, that one.
yeah.
It's like the same, but got 21, so we're right.
We are right.
Wait, hold on. The newtons or?
You have to change the centimeters to meters. So you gotta turn that over. And so if you did what I think you did,
Yes.
you got 21. Ugh. And what's the unit?
Long Island supremacy is Long Island is kind of crazy.
Okay, don't erase. Now we're gonna do 23.
Do it over.
Do we need another color?
Yes.
Green?
Purple. Yes, that one. That's what the last one. Only pastels. Oh my
See it? Okay. For the spring in the previous problem, you ready? Determine the amount of work. Uh-oh. I don't know if we actually got all the formulas for this, but I'll help you. Done to stretch that spring and the power required. We gotta, yeah. If the spring is stretched, the amount stated in 175 microseconds. In other words, the time is 175 microseconds. Oh my goodness. This is for the spring in the previous problem. Now here's the equation that you don't have yet. Work equals, we did talk about it back in chapter 2 when we talked about dot product and scalar and cross products. You remember that formula for work? You probably have it.
Should be. That'd be how many seconds?
Oh, 4 seconds.
We haven't used it much.
Oh, the W equals, is it N?
So it's W equals FD. Dot D. Okay, but since we're just using a,
Why is it dot?
because you want the force in the direction of the motion, not perpendicular, which would be
Oh,
cross.
is that the dot? Okay.
Dot product. Okay. And so we know the force is what? 21 newtons, right? And what was the distance? Point,
Oh, 12 centimeters.
yeah, or 0.12 meters. Okay, so what will the work be then?
Oh my God.
You get 2.52, and what's the unit? Okay, well, actually, that turns out to actually be a joule. A newton meter is the same thing as a joule, because a work is a form of energy.
Whoa.
Yeah, pretty crazy. Okay, and we had an equation for power. Do you remember what it was?
Power equals U over T.
Energy.
Okay, and in this case, the U is the amount of the energy is the work. Okay, so in this case, we're using the work over the time.
Oh, we still have.
Oh, look at it, we have the time.
What is, can you convert from milliseconds to seconds?
Yeah.
0.175 seconds.
Did you go 1, 2, 3, right? shorter than your reaction time. And so we're going to have that divided by 0.175. So power equals,
Yeah. Does that also come out in joules?
no, what's the unit for power?
Oh, wait, hold on.
Oh, it's W.
Yeah, whenever I say what's the unit for power, I'm actually telling you what. Watt is the unit for power. Yeah.
I like the purple. Purple's pretty.
I think the purple might be electric.
I don't know, that's cyan though.
I think we should ask the boys what their favorite color is.
That's what-
Okay, well, we can ask them.
I
That's
know
why
that
they have to have a kid.
The girls want to know what y'all think is the best color that we've used so far.
Best color.
It was the light blue.
Light blue,
I totally agree.
not the dark blue, huh?
I like the.
Not the lavender? Purple.
Yeah, lavender.
Well, Brian calls it purple because he doesn't.
That's wrong. It's lavender.
It's lavender, there's a difference.
Cameron, what do you think? Favorite color?
And
like the
it's
purple.
She said purple.
Yeah,
Okay.
Lavender.
I'll leave the one person on the blue side.
No, I'm on the blue side.
The light blue or the darker blue?
Light blue.
Okay, go back and sit down for a minute. Erase and sit down.
Can we move it back?
Ooh. Actually, come back to page 144. Okay, 144. I think what I'm going to do is share the screen again. And clear this. And y'all are going to tell me what to write. And this is example 5.4, but I'm going to change colors. I'm going to go to green, dark green, because I'm a pretty. Okay, it says, in the old days, before air-powered toys became popular, they've always been popular, you know, like using a straw and spit wads, that's air-powered toy. Anyway, a toy dart gun contained a spring that was compressed when the dart was inserted. Didn't the Nerf ones we looked at have springs in them?
Yes.
Oh.
And air.
And air, you're right. Okay, well, this is just the spring, okay? So assume that such a dart gun contains a spring with a constant K equals 75.5 newtons per meter, rather. When the dart is inserted into the gun, the spring is compressed 11.5 centimeters. So that's the actual delta X. That's pretty far. And that comes out to 0.115 meters, right? Assuming that 85% of the potential energy in the spring is converted into kinetic energy. I'm gonna write it as PE, goes into kinetic energy. We'll get the right variables in a minute here. And the dart has a mass of 15 Gs, 15 grams. Determine the velocity of the dart as it exits the gun. They just give you the spring constant, how far the spring moves, the efficiency of the spring, and from that you're supposed to figure out the velocity of the dart. And you do it. What should I write down? I need to change one thing, convert. What do I need to convert?
Grams.
Grams, okay, so that's gonna be what? Kilograms, right? Okay, so from the,
It's
In-
0.015.
thank you, yes, you're right. Undo. 0.015. Okay, for one thing, I'll write some equations down, okay, that I think you might want to use or just possibly use. Okay, delta x, and we have u with the e equals 1/2. What was it? K. And then delta x squared. And then we also have efficiency. Well, no, let's see. We have UK equals 1/2 mv squared. Okay, potential energy right here is this UE right there. And this kinetic energy right here is that right there. So what can we find out first? Y'all can chime in if you want to from your homes. What's something that we can find? Do we need to find the force? We're so quiet. Can we find the elastic potential energy? Do we have K and delta X? Yeah, so let's do that. Let's find that. Okay, so I'll change colors. Brown? No. Orange? No. Yellow? That'll be hard to see. How about maroon? We'll try maroon. Okay. So what I'm going to do is I'm going to find UE. That's kind of like brown though, doesn't it? Oh well. 1/2 times 75.5 times 0.115 squared. Okay, let's see. Here's the calculator handy. You know, find that for me. 1/2 times 75.5 times 0.115.
Hopefully this is right. 0.499. So it'd be 0.5.
Joules. Anybody want to double check that? Okay, so that's the potential energy of the spring, and 85% of that, 85% of 0.5 gets turned into the kinetic energy, which is UK. And so what is 85% of 0.5? How do you find that out? Multiply 0.5 by 85? Now you got to change the percent to a decimal, so 0.85 times 0.5 would be something, I don't know.
0.425.
That's what I thought. 0.425, that's the kinetic energy, because see, remember it said 85% of it was turned into kinetic energy, and that kinetic energy is equal to, or you could say the 0.425 joules is equal to 1/2 mv squared. Do we know the mass? The mass right here. So do you think we could find V? What would V be equal to? What would we do to find V? We would have to take the 0.425 joules and multiply it by 2, right? And then divide all of that by, by what? By the mass, which is 0.015. And then take the square root of that, right? Then get that. There. You take the square root of all that.
It would be 7.2
meters per second.
Yeah.
Let's see. Oh, look on page 144. That's what they got. So that was pretty interesting, I think. You can just know a little bit about your spring, and you can figure out, even if it was 100% efficient, you can figure out the maximum velocity, right? By just using the whole amount. Because all this energy got converted into that, or 85% in this case. Okay, so now what we're going to do, I'm going to stop sharing. Here we go. Look on page 145. We're going to read some more. And most of this should be pretty much review. Okay, so let's see. I'll get Kate to start reading at Radiant Energy. We're on page 145, guys. And read loud so they can hear.
Radiant energy, also referred to as electromagnetic radiation, is the energy in electromagnetic waves traveling through space or through media such as air or glass. This type of energy includes all visible and invisible light, as well as radio waves, microwaves, and a number of other kinds of radiation. The only difference between these different kinds of radiant energy is the wavelength of the radiation. The full spectrum of wavelengths of radiant energy is called the electromagnetic spectrum. Some of the most commonly discussed regions in this spectrum, along with the approximate wavelength ranges for each region, are shown in figure 5.10. A closer view of the visible light portion of the spectrum is shown in figure 5.11. This graphic displays the 6 standard colors in the visible spectrum: red, orange, yellow, green, blue, and violet, along with approximate wavelengths for the transitions from one color to the next. I've been describing radiant energy in terms of wave properties. This is common because this radiation displays all of the properties we usually associate with wave phenomena. Thinking of this radiation as waves was universal during the century leading up to 1905. But as you recall from earlier in this chapter, Einstein demonstrated that energy is quantized. This means that since 1905, we have also had to think of radiant energy in terms of discrete packets of energy. In 1927, the great American chemist G.N. Lewis dubbed these energy packets photons. We now think of light as both wave light and particle light in different properties. Wave or particle will be exhibited by radiant energy in different types of experiments. This strange physical reality usually now goes by the phrase dual nature of light or wave particle duality.
Okay, so remember G and Lewis, y'all remember doing Lewis dot structures in chemistry? Same guy. He's one that gave the name of photons. And what's interesting is all scientists across the world just accept the fact that that light acts like a wave and a particle, even though by definition, a particle is not a wave and a wave is not a particle. But somehow light is both. And you can't demonstrate both of those qualities at the same time. Whatever experiment you're doing, you'll either see the particle behavior of light or you'll see the wave behavior of light. And even if you try to adjust the experiment conditions, you'll still get one or the other, not both. But they still have proved that light has both these qualities. Pretty weird. And some people say, they try thinking that's impossible. There's got to be something wrong with this. And so a lot of people have tried to figure out, is it a wave, is it a particle, which is it? And they've spent a lot of money, a lot of time, and we still have this dual nature of light. Which I think is interesting because in the Bible it talks about Jesus being the light of the world and God created light, and Jesus is another God, or Jesus, I guess we talk about, is 100% man and 100% God, has that dual nature. And light is has the fastest speed of anything in the universe, right? And so what that means is light can travel, but when you get into relativity, the faster something goes, the slower the time goes. And so light, for light, the whole universe all happens in a single instant. And that's kind of God-like too, in a way. I mean, there's a lot of parallels. The more you study, the deeper you go with this, there's the more parallels are. It's really amazing. So anyway, and I don't guess we should be too surprised at some of that, but it's still cool. Let's see. Lewis, would you read the first paragraph on page 146 to finish up that section?
The energy in a single photon, a quantum of radiant energy, is given by the Planck relation equation. In any type of wave, the frequency of the wave and its wavelength are inversely proportional, lower frequencies corresponding to longer wavelengths and vice versa. Thus, for radiant energy, the shorter the wavelength, the higher the energy is. This is why short wavelength radiations such as X-rays and gamma rays are harmful to organisms. The more energy contained in the photons, the more damage done to the tissue, to tissues absorbing the radiation.
Right, and so you mentioned equation 5.1, so go back to page 138. And it's the E equals HF at the bottom of page 138. And so E, you think of energy having a frequency, but if you replace that with E equals hv over lambda, you got wavelength and the energy of one particle. So it kind of combines the particle wave nature into one relationship. And we use that equation a lot in chemistry. So he doesn't really go into that much more here. What else was I going to say though? Oh, when you're talking about sunblock, they talk about UVA and UVB. You ever heard of that? Okay, what's the UV stand for? Ultraviolet, which is higher energy than visible light. And that's what we're trying to protect ourselves from, because it has that energy that can do damage to tissues. And I think the A is lower than the B. I'm not quite sure on that, but one of them is like right close to violet, and then the other one's higher up in energy. And then you have infrared, which is lower energy. Okay, so let's see. Catherine, would you read electrical and thermal energy? I'm sorry, no, read chemical and electrical and thermal.
Chemical potential energy. This energy is the sum of the kinetic and potential energy in the atomic bonds and motions of atoms and crystals and molecules at the atomic scale. In exothermic reactions, the chemical potential energy in the molecules is released as heat and light.
Okay, and let me ask you there, can you think of an example of chemical potential energy? That's pretty common. What about you guys at home? Anybody? An example of chemical potential energy? The most common example they give is batteries. Batteries have chemicals in them. If you dissect it, you can see it's like a paste that has chemicals. And when you run a current through it, it causes reaction to happen. And the chemical bonds, you have chemical potential energy. Another example is just when you have a chemical reaction that gives off energy. You know, when you mix vinegar and baking soda. Vinegar and baking soda, you got some energy there. So all of that's chemical potential energy. And also like in gasoline, they talk about in order to make your car move, you got to have energy. And the energy comes from the gasoline. So the gasoline has chemical potential energy. And when it's combusted, it's converted into heat, which is that energy is converted into the pistons moving, which is converted into your wheels turning. That's pretty simplified, and I'm not sure if it's totally accurate, but you get the idea. It's always converted. Okay, continue, Catherine, with electrical.
Electrical energy. This is energy flowing in conductors, such as from a power station to your house for powering your appliances. We'll explore the details of electrical systems and electrical power in more detail in chapter 13.
Or, since we probably won't get to it, you might get to it in college if you continue into a science background. Okay, how about thermal energy? Yeah.
Thermal energy refers to the sum of the random and disorderly kinetic and potential energy in a substance at the microscopic level. The warmer a substance is, the more thermal energy it possesses. In solids, thermal energy can be carried by elastic waves of elastic deformation that propagate through the material. These waves, or wave packets, since they are quantized like photons, are called phonons. A phonon traveling through a crystal lattice is depicted in figure 5.
And I haven't heard of phonons anywhere except from John Mays. So I don't know if you'll run across it in college or not. He apparently thinks it's pretty fascinating. I think it's pretty cool because he talks about it in the chemistry book too, in one of the little special sections. The thermal energy is usually connected to temperature, because like if I have, you have liquid in there? Let's say well, not very much, but say it was full, and you looked at all the water molecules and how fast they're moving, and maybe even the molecules of the cup. I'm holding this, it's a water cup of Sierra's. And so the thermal energy would be the energy of all the particles in it, okay? But if I talk about just a cup here and say I throw it to Maddie back there, then as an object, you'd just be talking about its velocity, its kinetic energy as a macroscopic object. So if you're looking at it as one big object, it's the mechanical energy. But if you're talking about the energy it holds with all its particles, that's the thermal energy. Like I said, it usually is related to the temperature. Okay, then, yeah, no, they talk about internal energy being the temperature, thermal energy. Well, they're pretty related. Let's see, Brian, why don't you read internal and nuclear and acoustic?
The internal energy of a substance is the sum of the kinetic energies of all of the particles of the substance. The internal energy of a substance is a function of its temperature. We will examine this term more closely in chapter 11.
Okay, let me interrupt again. Okay, so they made a distinction there. The thermal energy was the sum of the kinetic and the potential. And then the internal energy was just the kinetic. And the average kinetic is related to the temperature. Okay, nuclear energy, Brian?
This energy released from the nuclear processes such as nuclear decay, fission, when the nuclei of atoms are split apart, and fusion, when atomic nuclei are fused together. All of these processes convert matter into energy, a topic we will address later in this chapter.
Okay, an example of that, like in nuclear decay, you've got nuclear or radioactive elements in the ground, and they're giving off energy as they decay. And that's part of the reason you have the Earth is as warm as it is. Okay, when they first were looking at the temperature of the Earth geologically, they were thinking, okay, it used to be a molten ball spinning in space, and gradually it cooled off and hardened and became this temperature. And when they did that with the math, they said it shouldn't still be as warm as it is now. And then they finally realized, oh, that's because you still have this radioactivity going on, giving off heat. And so it still has some heat in there. Okay, acoustic sound energy.
This is the energy carried in sound waves, such as from a person's voice, the speakers in a sound system, the shockwave of a sonic boom, or the noise of an explosion. Since sound waves are moving air molecules, this is really our particular form of kinetic energy.
Right. Okay, sometimes it can be used as a weapon, and seen that before. So like, either really high pitch, or sometimes if it's just really loud, it can like break glass and throw you back and all that kind of stuff. Okay, then they talk about on the next section is processes of energy transfer. The good thing on page 146 is we didn't have any more equations there, did we? This is just kind of an overview of different types of energy. And then he gets into this bit about energy being transferred. So we have all those types of energy that we looked at on page 146, and then radiant energy on 145, elastic potential energy, mechanical energy, gravitational potential energy, kinetic energy. And those are just most of them, it's not everything. Okay, now we're going to get into what's called work, but work is not a type of energy, it is the transfer of energy. Okay. He says two very important processes of energy transfer are work and heat. Okay, so let's see, somebody else to read. How about Maddie back there on top of page 147?
Work, W, is a mechanical process by which energy is transferred from one object or system to another. When an object possesses energy in one of the other forms described above, we can say that the energy is a property of that object. But objects do not possess work like they do other forms of energy, and work is not a property of an object. Instead, one object does work on another object by applying a force to it and moving it a certain distance. When an object does work on another, energy is transferred from the first object to the second. Work W is defined as the scalar product between the two vectors force and displacement. Remember, the scalar product is explained in section 1. The role of the angle between the vectors f and d is demonstrated by our friend Mr. Breen in figure 5.13. When a vertical force is applied to a bucket to lift it, the angle between F and D is 0. This results in a maximum of work because cosine theta equals 1, and the product of FD cosine theta is equal to F times D, its maximum value. However, while carrying of the bucket at a constant speed, no work is done on the bucket because of the displacement of the bucket and the force applied to it are at 90 degrees, giving cosine theta 0. Of course, while carrying a bucket, your body is doing work, but the work is not being done on the bucket, and the bucket is not getting any energy.
Okay, let's stop for a minute and think about that. First of all, you can see why he calls him Mr. Green. That's kind of cute. And so he refers to it like you think picking up a bucket of water, that's hard work, right? It seems like you call it hard work. And the work is the fact that you're applying a force to it, and the force is being applied over a distance. Okay, and then when you're carrying the bucket, you're still applying a force, but it's a force up. Now, that's the only force you're applying is the up force. Now, as you walk, you're having to push on the floor to go forward and that kind of thing, but you're not pushing the bucket forward. You're just carrying it with you. And so you're not doing any work on the bucket, even though you're still applying a force there. Same thing as if I'm pushing against the wall really hard. I can be applying a lot of force and get tired, but I'm not doing any work because there's no motion. Work only occurs, this kind of work, mechanical work is only done when there's actual motion. And it's only the amount of force in the direction of the motion that counts toward the work. Okay, read that second paragraph.
Again, work is an energy transfer process. When Mr. Green lifted the bucket, the chemical potential energy in the muscles of Mr. Green's body was transferred to the bucket in the form of gravitational potential energy. In fact, consider the equations for U, G, and W with this in mind. The UG of an object is mgh, or Fw times h, the weight times the height. To lift an object, you have to apply a vertical force to it equal to its weight. If we call the distance the bucket moves h instead of d, then the work done on the bucket is also Fw times h. The work done on the bucket is energy transferred from Mr. Green to the bucket, and the bucket then possesses the same amount of energy in the form of gravitational potential energy.
Okay, and so what he really is trying to push here is that objects, energy is a property of an object. An object can have energy, but an object cannot have work. An object does work or is worked upon by something else. That makes sense? And when you pick up a bucket, you're converting the work you do into the potential energy. The work you do is a certain amount of energy that comes from the muscles in your body that's transferred to the bucket in order to give it potential energy. Now, if you drop the bucket, then that potential energy can be converted into kinetic energy when the bucket falls, right? Or you could pour the water into a turbine and cause another way of, to transfer energy. How did Mr. Green have chemical energy in his body? Where did that come from? What gives you energy? Food, right? And so there's chemical energy in the food. Where did the food get its chemical energy from? Depending on whether you're a meat eater or an herbivore, let's say you ate a hamburger, you're talking about the meat in the hamburger, that came from the energy in the cow, but the cow got it from the energy in the grass, right? Or if you're eating vegetables, then you're getting it from the vegetables, which got it from, what do vegetables get their energy from? The sun, right? The sun gets its energy. Usually we just stop there and say that's just from God or something. But I mean, you can really take it all the way back to the Big Bang if you wanted to. Because at some point there had to be gravitational energy causing gases in the universe to collapse onto each other and start all this, formation of the galaxy and planets and all that kind of stuff. And so you can take it even further back, but it's always being converted, and the total amount of energy in the universe stays the same, with a slight caveat for that, but another force. So. Okay, and then they talk about heat. I think that's where I'm gonna want to stop, although it's still got time here. I'll just read that one. It says the term heat refers to another energy transfer process, like work with an energy transfer process. Well, heat is too. Heat is energy in transit, transferring by conduction, convection, or electromagnetic radiation from a hot substance to a cooler substance, and when a difference in temperature is present. Okay, in other words, like if you have hot water and you have cold water and you mix them together, the temperature is going to move from the hot to the cold until they're equal, right? But if you have two things of water that are the same temperature and you mix them together, you're not going to have a heat transfer. You have to have a temperature difference first to have that transfer. As with work, because substances do not possess heat. They used to talk about things possessing heat. When substances do, what they do possess after being heated is additional kinetic and potential energy that in their moving atoms, that is more thermal energy. So substances can possess energy, but they don't possess heat. It's kind of weird the way people use it normal day. It sounds like you would say that, but you don't possess heat. Heat is the transfer of the energy. Kind of weird. Okay, any questions on any of that? Okay, we're gonna get some historical stuff next before we get into some more math stuff, but I'll probably have y'all work some exercises before we get into any of that. So starting tomorrow, unless y'all want to start working on the board now. Yeah, we can go outside or something. What we got?
Can I go find Mr. Locker?
Yeah, 35, 40, got 15 minutes. I got done early in chemistry too. You can play darts. Cool in chemistry. Okay, guys, so that's all we're gonna do, as you heard me say. And since y'all can't join us in darts, you can hang up if you want to, or you can watch the rest of the class. So it's up to you. Yeah, there goes Lewis. He's quick to hang up.
Oh, they all.
Bail. Did they even wave or anything? Gosh. How rude.
Mrs. Welcher?
Yes.
Can I go find Mr. Locker?
Yes, you can. I thought I said yes. I didn't.
Oh, I didn't know if you were talking.